Hi, welcome to Teardown Tuesday. You don't have to worry about me getting lost in this video because I've got an EPIRB, or an electronic position indicating radio beacon. One of these emergency beacons that you carry when you're hiking or you're out boating or something like that. If you get lost, get in trouble, you're about to die, flip the antenna, push the big red button, and hopefully somebody comes to rescue you. Well, that's the plan anyway. I actually know quite a few people who've been rescued by one of these things when they're hiking or canyoning or doing various things like that. Very popular little devices and life-saving devices. This is the older model EPIRB. This is the Minisat Alert personal EPIRB from KTI. It's an Australian company, designed and built here in Australia, designed for our local regulations, because all countries have different regulations for these things. This is actually an EPIRB, but they're also known as PLBs, or personal location beacons. EPIRBs are traditionally designed for the marine environment. They can be floating, self-righting with an antenna and saltwater activated and all that sort of stuff. This one is designed to carry in your backpack when you're hiking or something like that, or maybe on a little boat or something like that. It's not a true marine one. It's a personal locator beacon, effectively. So this is the older model, 125 megahertz. There it is, 125 megahertz / 243 megahertz analog system. They've actually phased this out now, so I think if I activated this, I'm probably not going to get rescued here in the lab. In fact, the signal probably wouldn't get out of the lab here. You have to have pretty good conditions for fairly open sky for these to be picked up by the satellites. Now this one's compatible with the COSPAS and SARSAT satellite system, and it's the older analog system. The newer digital system is 406 megahertz, and that sends out a digital signal in addition to if you've got a GPS equipped unit, it can send out your exact GPS location. But this one, even though it's analog, I think the search and rescue helicopters, when they come out to rescue you, still have a 121.5 megahertz radio location finder on them, so that they can pinpoint your location. Because when you activate one of these and a signal is picked up by the satellite and they triangulate your position, it is very rough. They can't actually get your exact location from that. So when they call the helicopter, they fly out, and then they use a radio finder in the helicopter to narrow down your exact location. So that's with these older analog ones. But the newer digital ones, they can send out your exact GPS position, bang, they know exactly where you are, sends out a digital code that you pre-register, and they know who owns it, and they can contact your family to get additional info of exactly where you've gone and all that, what equipment you're carrying, all that sort of thing. This is the older analog one. We're going to tear it down. Could be quite interesting. I wonder what's inside this thing. It's waterproof, it's shockproof, it's got a 10-year lithium battery in there. But I will try not to set the thing off. Let's go. And I've got to thank Julie Burton, who's a canyoning friend of mine, for giving me this unit for the teardown. She doesn't need it anymore. It's an old one she used to carry on her canyoning and hiking trips. So thank you very much, Julie. Now, as I said, it's a KTI, manufactured by Kinetic Technology International here in Australia, made in Australia, not Austria, and its battery has expired July 2011, but it's still going to work because basically these have a 10-year lithium battery in here. I think this has a C-size lithium battery in it, and they will typically have a 10-year shelf life, but they specify the replacement time as half of that, or 5 years. So this one the battery would have been installed, and it was probably manufactured around 2006 or thereabouts, hence the July 2011 replacement date. And it is the Minisat Alert personal EPIRB, 121.5 megahertz, 243 megahertz analog system. And there isn't really much to them at all. They're very simple units. They've got some instructions on the back here, how to operate. Break the seal by raising the aerial and then fully extend upright, press button until red light flashes. On land, place in a cleared area away from people and obstacles. At sea, attach beacons to your buoyancy vest. And there you go. And of course, it's got a test mode, which we can try out because it doesn't transmit in that mode. And as you can see, it hasn't been used. Julie's never used this thing. Break seal to raise aerial, because the whole idea of these is hopefully you never have to use it. Because if you have to use it, well, you know, it's going to cause a lot of grief to somebody, especially yourself, if you've done an injury or something like that. So it has never been broken, because if you want to use it properly, you just extend the antenna up like that and push the button and it will transmit. But it has a test mode. If the antenna's down like this, we can just press it. Here we go. There we go. So presumably it does like an actual self-test, and maybe you know, actually transmits internally but not to the antenna. It disconnects that, of course, because you don't want this thing actually transmitting to the antenna just for the test. So maybe it's got a system in there that actually transmits the signal, something that reads it back and then verifies it. So I'm guessing that there's a micro controller in here or something that that's fun. There you go. And so yeah, it's probably got a micro in here to do that self-test functionality, because I'm sure the self-test is just more than flashing an LED, you know, and the battery's working. I think it's probably a bit smarter than that to make sure that it's still operational. Anyway, it's got a lanyard here on the bottom. You open it up, so you can attach a lanyard. Oh, warranty void if broken. We love that stuff. And apparently you can, these are repairable and you can replace the batteries in them. So presumably there's a screw under there. If we undo that and that, we'll probably pop that bottom off, probably O-ring sealed around there, but only one way to find out. Let's void this warranty, you bloody ripper. Here we go. There we go. There's the screw. Ta-da! Let's open this sucker up. And presumably there will be a some sort of way to detect that that antenna is down as well. Because, oh, hey, there we go. Oh, look at that. Oh, man. Check that out. Okay, so that obviously goes right up through there and goes into that metal thread. I think I can see like a metal threaded insert up there, so it goes all the way through and probably keeps it all together like that. So that's rather interesting. This one doesn't, oh, yeah, there we go. Yeah, two of them. Got two long rods. Oh, that, yeah, there we go. We've got some O-ring seals on there, and presumably it comes apart. Maybe I have to break off this tape around here or something. Oh, there's the antenna, by the way. It is an extendable antenna like that. So I'm pretty sure we won't transmit on this thing if we just disconnect the antenna, and it's not going to get out of the office anyway, I think, even if the antenna was extended. So we should be able to measure the output of this thing. So let me actually take this tape off, because I think that's probably holding the two halves of the case together. Ta-da! Be able to. It's a bit springy. Bit springy, but it is coming loose. Yeah, see the copper shield in there. Well, I was expecting this board to be bigger, but check it out. It's not that big at all. All circuitry is under that what looks like copper shield there, and there's the, looks like two C-size batteries down in the bottom. Yeah, here it comes. It's just going to pull out. That's it. Too easy. And there's our piezo transducer down there that makes the beeping noise when we test the thing, but geez, it's not much to it. And I was spot on with the date. There it is, May 2006, 5 years, replaced 5 years after the date of manufacture. So we've just got two C cells. Looks like it maybe has some protection stuff in the top. Let's have a look at the board, which is rather interesting. The first thing to note is a standard PC test socket here. These are for 2mm probes. You can buy these from DigiKey. They're just off the shelf stuff. I've looked at using these before, and they're designed for 2mm, like actual, they're the exact width of your multimeter probe, so it can just plug directly into that. So, and look at that spring there. They've got this little, well, it's not actually, it's kind of like, it looks like it's a spring, but it doesn't do anything in that respect. That is clearly the sensor that is using to detect whether or not that antenna is up or down. So maybe it's some sort of, capacitive coupling thing or something like that, because when you raise that antenna, it's not going to physically move that spring at all, and it is electrically connected. Is that grounded there? It looks like that point is grounded. They may still be using that as a capacitive coupling system through to the antenna, so the circuitry may sense the antenna and measure that first before switching on a solid state relay or something like that to output the RF signal to the antenna. So there's something going on there. It's rather unusual. And there's our 121.5 megahertz crystal, which is used for both frequencies, of course. The other one is just double that frequency, and yes, it is held down with some sort of epoxy adhesive or something like that, because this is designed to be shock proof. So we can easily just slide that off there, and bang, we've got our board out of there. And of course that is all O-ring sealed down in there, because this thing is waterproof to like 3 meters, so it's got various O-rings over the place, and that's rather nicely designed. And we've got our board to take a look at that. We have to get rid of that shield, no problem. Should be easy peasy to get off. Just heat up the copper. I could cut it, of course, but easier just to heat it up with the iron and then just pull it off. No drama. Got to have that third hand, and I'm trying to get it on camera here, so hate trying to get things on camera. Never works. Ta-da! And here's the board, and as predicted, there's the microcontroller. It's a Motorola MC68HC705 with its own local oscillator. Is that 20 megahertz, I think? Or is that, could even be 2, no, that's 2 megahertz. There you go, it's running at 2 megahertz, and the rest of it is pretty much all analog / RF stuff. There's the button, of course, which the test / activate button from the front, and here's the antenna output up here, and the crystal actually connects to the other side there. So there's the 2 points for the crystal. So there's going to be an RF oscillator around here somewhere based on these transistors. These are all going to be transistors of some description, and they've got to modulate the signal as well as double it, because it has to be doubled to that 243 megahertz as well. So that's clearly all done in the analog domain, which I guess is not really surprising, because there's not, why do it digitally? Really, I mean, the new 406 megahertz digital PLBs, of course, would be much more complicated and high-tech in terms of digital control and stuff like that. But in the end, it's just got to have 121.5 megahertz oscillator. It's got to have a doubler in there to generate the alternate frequency, and some sort of modulation thing, probably, I don't know, happening around here perhaps, that this would be the RF transmitter. I would suspect, based on the size of the device, it's physically larger. These things output, I believe, an RF signal level of about 150 milliwatts or something like that. So, it's not terribly high in the scheme of things, but they obviously need that slightly larger output transistor there to do that, and the rest of it is, I would presume that's modulation, because that sort of comes from the microcontroller down here into this area around here. So there's probably got some switches and some probably another local oscillator or something to modulate the signal on top of that. But yeah, there you go. It'd be interesting to see the schematic of this thing. You could of course reverse engineer it. It's only a very simple double-sided board, but it would take a significant amount of time. So, but if anyone has a schematic for one of these things, please post it in the comments, because it would just be interesting to see the arrangement that they've used to get one of these things working. So there's not much really left to tear down on this thing. That's pretty much it. So we may as well activate it. Let's go. So what I'm going to do with this is I'm actually going to eventually disconnect the antenna, because I don't want to accidentally transmit 121.5 megahertz at full power, even if it is inside the lab here, because I believe commercial airliners can still pick up this distress frequency. I'm not sure if they still actively monitor it or not, but they have the capability to do that, and have done in the past, in case the satellites don't actually capture them. But what we can do is we can hook up a scope to the antenna output here, and we can capture, we can have a look at the waveform and capture the signal. So what I'll do is I'll do it first with the antenna down, and we'll see if it's actually transmitting anything to the antenna at all, and then we'll actually disconnect the antenna and then activate it again. And then it should do its full activation, and we should be able to capture the output signal and take a look at it. Now I just noticed this. I'm pretty sure, as I mentioned, this is the output power transistor here, driving, we've got a trimmer cap here, just driving the antenna here. But look, then we've got it AC coupled. The output to the antenna here is AC coupled, and it goes into this separate transistor arrangement over here, which, as I said, that metal bar there somehow capacitively detects whether or not that antenna is raised up or not. So I think that's what that circuitry there is doing. It actually detects whether, so the microprocessor, before it starts to transmit, it probably reads that the antenna, it checks to see if the antenna's down. If it is, it goes into test mode, and it probably does that via that circuitry there, and it looks like it just goes straight back into a pin of the micro. Okay, so what I've done is I've reverse engineered this little section around here with what looks like 2 transistors and that AC coupling cap to the antenna there, and unfortunately it's not very exciting at all. Here's the antenna. It's got a inductor on the output. This is the RF transmitter section, and it's and picks off that, AC couples it. There's a diode clamp there to ground. There's a voltage divider there driving an NPN transistor with a capacitor on the output going directly to the pin on the microcontroller, which presumably, of course, has an internal pull-up resistor. That's all there is to it. So they've clearly split this board into 2 halves. Here's the RF oscillator stuff around here, all in this section, and then the RF transmitter up here. And it's clearly divided by these digital lines running through here like this. And the only coupling between this part of the circuitry on the left here and the RF part on the right is the part we mentioned with that detection circuitry with that AC coupling cap picking off the signal from the antenna. And the other one is this little resistor in here, which couples this part, which I believe is the modulator, over to this RF section over here. And that's really, there's another control signal coming in here like this in there. So there's a digital control signal there, and that probably shuts the transmitter off and on, or does something. Perhaps it's another, maybe it's a digital modulator, some sort of test thing. Maybe it's got something to do with injecting a signal to test that the antenna's up or something like that. I'm not entirely sure. And there's probably something else which looks like it another control signal runs into here, something like that. That's probably to switch between the 2 frequencies or something. So there needs to be a control line coming from the micro. You can see that there, and then this resistor going into this part of the circuitry around here. And as I said, this is the oscillator part of it here. So that's probably the control signal. Scope time. Okay, I've hooked up the scope to the antenna output here, and watch this, I can make it come and go. There we go. That's my 50 Hertz AC coupling from the antenna. I put my hand on the antenna there and whoo, there we go. Isn't that fun? Absolutely nothing to do with the operation of this thing, but just thought I'd show you that. It's neat. All right, let's see if we can capture something in test mode here. I have no idea what it's going to give out or do anything at all, or how to trigger. That's why you've got to experiment with these things to find out. So I've got the channel 1 connected to the antenna output there, single shot capture. We've got 100 milliseconds per division, horizontal, and 1 volt per division vertical, set to trigger just above that. So let's give it a go. Let's press the button and see if we can trigger something. Oh, there we go. We got something. There we go. We got a spike, and then boop, another little spike. So that's clearly above 1 volt per division. So let's set it to 5 volts per division and try that again, shall we? Here we go. Let's set the trigger point a bit higher. There we go, about 2 volts or something, and trigger, bang, there we go. So at 5 volts, that's the battery voltage. Clearly it's applying something to the antenna there. So let's do that again. Let's go for a longer time base, 500 milliseconds per division. Let's try it again. Push the button, bang, 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 bang. There we go. We got a bunch of pulses. We got that first one, positive. Got another one going negative there. That's a huge, is that something? Yeah, something's going on in there. We've got an RF packet. There we go. The sampling's quite poor because the memory depth isn't long enough here. This thing hasn't got enough memory at 4 meg sample memory. But that is, we can have a look at that in more detail later because that is quite high. So we can set our trigger level higher than that and capture just that RF packet. All right, so we've got the whole thing on the screen here, and this is like the switch on pulse, presumably when it like switches on the RF stage or something like that. So that's just a spike. As we saw, it's, you know, there's nothing much doing there, but then we've got this RF pulse here. We've got another one here, 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 here. So it does 5 RF pulses by the looks of it, and then presumably switches the antenna off again. That's what happens in test mode. All right, let's see if we can capture this RF waveform. So I've set it to 5 volts per division now, the trigger level, at about 10 volts. So because we know that that start and end pulse only went to 5 volts, so we want to trigger above that only on those RF pulses. I've gone faster on the horizontal, 100 microseconds per division. So just as a rough guess, so let's, got it on single shot capture mode. Let's do that. I'll press the test button. Bang! We captured it. Too easy. There you go. So it looks like it's about 10-15 volts. This is 1 mega ohm input impedance, by the way. I haven't got this like 50 mega ohms input impedance. So there's the waveform. If we zoom in and we'll turn on some measurements, bingo, 125.5. I think if we got in there a bit more precise, the frequency counter on this thing isn't the greatest from the measured data. So there you go, but that would be 121.5, of course. And if you have a look at the length of the burst here, 5 microseconds per division, 5, 10, 15, 20, it's about 23 microseconds or thereabouts RF burst at 121.5 megahertz. Let's capture that again at a much faster time base, 10 nanoseconds per division. Bang! It's still saying it's 124.5 megahertz. It's not 121.5. That's interesting. So maybe it offsets. It looks like that is the true frequency there. So it is offsetting that, I guess, so it doesn't accidentally transmit on the 121.5. So it tests it at 124.5. So with this coupling circuit here, I think what's probably happening is that when that ground-in bar is close to the antenna, of course, it's got more capacitive coupling. So when it does those test burst transmissions there, there is some capacitive coupling, and the amplitude is enough to either presumably like not or switch on or switch off this transistor, which the microcontroller can detect at those lower 23 microsecond burst time periods, which we looked at. So it turns on the RF transmitter and sees, and this circuit just picks up the coupled AC coupled signal from the antenna, which the antenna's characteristic is going to change depending on whether or not the antenna is vertical or whether or not it's laying flat right against this grounded bar here. Now what I'm going to test is that modulation point down, well, what I thought was a modulation point coupling over to the RF stage. So I'm going to probe that at the same time as doing the test signal. So let's give that a go. Let's single shot capture mode and press the test button. Bang, and way, there's the, whoa, it's way up there. Let's change channel. Looks like we've got to go down in channel 2. So there you go. Let's try that one more time for the dummies. Bang, there we go. Look at that. That is 5 volts per division. So that point sits at 5. It could just be coupling over, so I'm not sure what's going on there. But clearly that could just be coupling, possibly, between, yeah, obviously it's going to do that. It's probably going to couple over, so I'm not sure whether or not that green channel 2 signal is controlling that, or it's just coupling over. It seems to be sitting at 5 volts and then just couples. It seems to step down a bit there, so let's go out and at a longer time base, and let's try and capture that again. And there we go, I captured that at a long time base, and you can see what's happened. There's a slight change in that point there after the RF burst, so it's kind of doing something in there. I'm not exactly sure what that's telling us at this stage, but well, it's interesting. Now what I'm going to try is probe the output of that circuit that I reverse engineered, which goes back to the micro there, and I know that this is a 5 volt logic input signal, so I can set my vertical scale to 1 volt per division. So I'll probe that and let's have a go and see what we can pick up once again when we do the test thing. And single shot, test, boom, test mode, bang, there we go. So, can you see what I see? It goes from 0 volts to 5 volts and back down there, but there's also those green pulses that correspond with the RF burst. So let's once again zoom in on this. There we go. There's some, that's just coupling. I think we've coupled in some noise there. That's our antenna earth lead there, just picking up some of the RF, but that is supposed to be a digital signal if I probe that properly. Anyway, let's single shot capture that again. Go into test mode. Boom, there we go. So it drops down low. So that's actually detecting. So that's pulling it low. So it's detecting that there's that RF signal there. You see how it only goes low? Let's have a look here. See how it only goes low after the yellow RF amplitude there has ramped up to enough signal level that it actually detects, and then bang, it goes low. And trust me, all that waveform there is just RF pickup. That green signal is actually a digital signal. And just for those who don't believe me that that green signal there is being picked up by this antenna earth lead, because that's pretty much what it is when you're talking about RF stuff, I will get rid of that, bugger that off, and we'll use our little high frequency ground probe on there. They're a bit tricky to sort of hold in place, so I probably won't be able to get it on camera at the same time, but let's give that a go with exactly the same conditions and see what we get. Actually, it's not too bad at all. Look at that, because they've got that convenient via there that the ground connects into. So let's keep that on there, and then we'll single shot capture this waveform again, and single shot, push the test button, and there we go. Much reduced. We're still picking up some crap on there, of course, but as you can see, it's much cleaner now. And if you didn't believe me before, you will believe me now, that where you can see where once this RF amplitude ramps up to a certain signal level, that switches on the transistor here. Once it gets to a certain signal level, that transistor switches on. It's just an open collector output with a pull-up resistor there, so it switches low like that once it gets to the level, and that the microcontroller can then detect that there's RF on the output, so it can detect it's testing there that the RF transmitter works. And now let's probe this point in the circuit where a digital line comes from the microcontroller somewhere into that RF section. So I expect that to be some sort of gate impulse for the RF oscillator. Let's give it a go. And there you have it. It is some sort of gate impulse for that RF transmitter there. Once again, I've got the antenna earth lead back on, so we're picking up crap here. It's actually a digital, it's truly a digital signal here. This is a pain in the ass trying to probe. You know, if you're looking at signal integrity in an RF design like this, probing is absolutely everything. I mean, look at that. You would think that there's something wrong with your design when you get all this shit on it, if you don't actually know what's happening with your probing. Anyway, it's clearly some sort of gate impulse, but there's a long time there. By a long time, I mean like, you know, 7, 8 microseconds or something before it, by the time that goes low, before the RF transmitter actually switches on. But it is certainly some sort of gating type pulse. And there's another digital line which comes across over here like this. I'm not sure which way it goes, of course, but I'm going to probe that under the same conditions again and see what we get. Press the test button, bang. No, we're just getting noise on there, so it doesn't seem to be doing anything at all, really. That's quite boring. Not at all happy with that. There we go, we've got it doing something now. There we go. Okay, it's doing, okay, we've got a much longer time base there. So it does something over here when it switches on, and then it's really, it is doing, so it is some sort of test signal, which is rather interesting. Let's have a look at the frequency of that. 1.475 kilohertz there. Now this is interesting. When you can just see the yellow RF pulse there switching on, this changes frequency from, actually it's going down. It's going down. Hang on, I don't have to probe that anymore. What am I doing? No, it's 700. Look, it's going up in frequency as I go along. As I scroll this back to the start, if I go all the way back, look, it's going up in frequency. So that's the modulation tone. There you go. That is the modulation, the decrease in modulation tone. Bingo! From the microcontroller. So the microcontroller is doing that in software. It starts out at about 1.4 kilohertz. So bingo, we have found the modulation signal for, they use this for the homing. It's a decrease in modulation signal on the carrier. It starts off at 1.475 kilohertz. Let's call it 1.5. and then it slowly decreases in frequency. It's going down and down and down. 1 kilohertz. And then it goes all the way down to, when the RF switches on, bang, there it is. That's where you can see the yellow pulse there. That's the RF burst we've been looking at. So it gets down to 700 hertz. So it goes from 1.5 kilohertz down to 700 hertz. That's all being software driven, software timing in the micro. And then bang, after the RF burst there, then decreases again. And of course it goes through that 5 times. But this is only the test mode, by the way. So I would expect to see operational differences when we're actually transmitting a real signal. So that's probably all the signals. I was hoping to find that one. So that's probably all the signals I wanted to probe at. I'm going to, for now anyway, so let's go into, basically get rid of the antenna so it will think that you want to transmit for real, and let's actually transmit for real. So here it is. Let's break the seal. How easy is it to break the seal on this thing? Too easy. There we go. Lifted up our antenna. You extend it, and if we press that button, bang, it's going to transmit for real, because you can see the metal clip in there, so it's not going to get that coupling anymore, so it's not going to detect that signal using that coupling. I believe that, so it may still use that for something, but anyway, it's going to go, right, I'm not in test mode anymore, I'm transmitting for real. So it won't stop after, like, 5 seconds or whatever it has been now, and it'll transmit at full signal power and give the proper homing signal and all that sort of stuff. So what I'm going to do is I'm going to disconnect the antenna, of course, even though I don't think it's going to pick it up in the office here. There's all, it's got a metal roof and everything, so, I don't think the satellites, not that they can pick up this anymore, I believe. But just to be on the safe side, I will disconnect the antenna. Well, I don't actually have to disconnect the antenna. What I'll do is I'll just take the entire board out of here, and bang, we no longer have the antenna connected. So that shouldn't, it'll be transmitting, but it really won't be going anywhere. Be horribly, horribly inefficient by orders of magnitude. All right, let's transmit for real, shall we? I'm in trouble. I'm near death, and I've got to hit that magic button on my EPIRB. Let's give it a go. I'm probing the antenna output. We can probe other stuff as well, so here we go. There we go. It's now blinking and flashing, so it is definitely transmitting. So let's give it a go. Here we go. Ha-ha! Look what we have on the scope. Ta-da! We have bursts. We have RF bursts. Check it out. Look at that. So let's capture a whole burst. There we go. That one, of course, there we go. 121.2 megahertz. That will actually be 121.5 if the software frequency counter, the automated cursor-based thing, isn't the best, but that will certainly be 121 down at the lower time bases there. So bang, there we go. It might be spectrum analyzer time, actually. And I just did a quick check for what the modulation requirements are for this thing, and apparently for EPIRBs it must go modulate either downwards in frequency or upwards. It can be either anywhere in the range from 300 hertz to 1600 hertz, but it must have at least a spread in there of 700 hertz modulation. And if it's a PLB instead of an EPIRB, apparently that has a requirement of only modulating upwards in frequency instead of downwards. And of course the 406 megahertz digital models can still optionally have this 121.5 megahertz modulated carrier in here as a homing beacon that is still used by the search and rescue helicopters. All right, it's crude measurement time. I've got a just a flying wire here, not actually directly connected, but just coupled nearby to the antenna connector, and of course we've seen on the oscilloscope it's transmitting in those bursts, and I've got the Rigol spectrum analyzer set up, so let's check it out. And we've got the Rigol DSA815 spectrum analyzer here, and the dreaded auto button. On oscilloscopes don't like them, but on spectrum analyzers they're not bad for just getting a first whack at a signal there. And bingo, there it is. We're at a center frequency of 121.7 megahertz, and as you can see, it's jumping. It's not the usual, carrier, nice clean carrier with the sidebands. It's chopping back and forth because look at what's happening on the scope over here. It's jumping all around. So we can get a better look at that if we go into single shot capture mode instead of just continuous mode. So if we hit the trigger sweep button here, it gets us into the trigger sweep menu and mode. We're in continuous mode at the moment, but let's go into single shot capture mode, and bingo, we've captured that, and you can see our carrier here. As you can see, center frequency 121.53 megahertz. There it is. So we've got that, no problems. Let's go into trigger sweep again. Let's turn that back to continuous. Okay, it's jumping all around the shop. It's not the easiest thing to measure. Now let's go into span and let's take it out and see if we can get the 220 odd megahertz frequency. What is it, 243? Yes, 243 megahertz, double. Because I don't think this thing, there it is, bang. Because this thing, there's the alternate frequency of 243 megahertz. Now, I don't think it's actually got a frequency doubler in there. It just relies on getting the first harmonic there from the signal. So I don't think it actually jumps frequency to 243 megahertz. It doesn't double it. It just relies on the fact that that is a harmonic of that signal, and you can clearly see it there. And if we go back into the center frequency, we can bring that over. I can measure it again, of course, but where is it? 240, bang, there it is, 243 megahertz, or thereabouts. So there's our two signals which it's outputting. Now, let's see if we can have a look at the modulation on this thing. So what we can do here is actually go into what's called zero span mode, and that should allow us to look at, bang, look at that. We've got that, you can see it modulating, you can see the frequency there modulating, and if you remember from before from the oscilloscope shot, that's essentially the same waveform we got for the actual digital modulation signal. Alright, I'm going to use the demodulation function of the DSA815 here, so I've got it hooked up to some headphones here, and let me put the mic near it and you'll be able to hear the demodulated signal. So you can clearly hear the modulation repetition rate there of between 2 and 4 hertz is what information that I found, and that's clearly between 2 and 4 hertz, and you can sort of hear like a sweeping whoop 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 within that repetition rate. Now it's usually quite difficult to detect these burst RF signals on a spectrum analyzer like this, because there's all these frequency components that jump around in there and they're not actually real. So what we need to do is go into the bandwidth detection over here and change the video bandwidth like this, and if we lower that, we should find that, bingo, our signal or our carrier pops out of that just nicely. There we go. When we decrease it to a video bandwidth of 300 hertz, 1 kilohertz, it really, it starts to play funny business and go crazy like that. But if we turn it down, then we can actually see the carrier signal itself. And if we change the span, of course, we can, oh, no, going the wrong way, change our span, let's go up, up, way up, way up. And bingo, there we have our 121.5 and our 243 megahertz. We've got some other stuff jumping in here. I'm not sure what's going on there, but we can clearly see our two carriers. There it is, 121.5 and 243. Brilliant. And we should be able to get better performance on a spectrum analyzer that has gating capability for burst type signals. I don't think this Rigol one has it, or at least I haven't found it yet. Now if we probe this modulation signal we found before, and if we have a look at that, we can see, if we trigger off channel 2 here, there we go, trigger off channel 2, we can see our modulation signal. Okay, now let's actually have a look at that signal we had coming back before, if you remember, from the detection circuitry on the antenna. And I'm dual wielding probes here using my third hand, and there's the signal. The yellow one is the return from that detection circuitry there. Slightly out of phase, but it's the exact signal that's being inputted to the RF circuitry. So if we disconnect that and we actually have a look at what's happening here, the microcontroller is outputting the modulation signal through here, through some AC coupling, into the oscillator down here, which amplitude modulates it, and then it goes through the RF transmitter, and that's tapping off, and that detection circuitry is reading it back and feeding it back in, so that microcontroller knows that it's actually transmitting the proper location, transmitting that home-in modulation data, and presumably it'll, you know, stop flashing and or do whatever, you know, error, and if it doesn't detect that output signal. So it's when it's flashing like that, you know that it's doing that transmitting, and well, you know, somebody's going to pick it up and they're going to be on their way. So presumably, if you get nothing on the output, it means part of the RF circuitry is blown, and I presume it will turn off the flashing lights. And of course, there's no need to speculate about that. Let's actually test it. I've removed the AC coupling cap that detects the output signal from the antenna, and let's see if this thing actually it continues to flash the LEDs and transmits. I wonder if it does. Let's have a look. No. There you go. No, it's still doing it. Look at that. I have disconnected that AC coupling cap. I'm getting desperate now. I've removed the AC coupling cap, the 10K resistor, and the output transistor. So that open collector one. So it's got nothing to switch low with. So that pull-up resistor on the circuit there, if we remove that transistor, we remove the AC coupling cap, 10K, and the transistor, that should stop that. So let's do it. No, it's not detecting it. There you go. That's pretty conclusive that it doesn't check that output when it's transmitting. Oh man, it's still modulating. It's still picking it up on the scope. This is ridiculous. What's going on? Well, that's embarrassing. I was probing the wrong trace. I got mixed up on which trace was coming back. I was probing that second pin instead of the third one, which is the one that comes back. Anyway, we did prove there that you remove that output sampling there, that output detection circuitry, and it doesn't care about sampling that during the transmission period. And I've replaced the components, and now I am probing the correct pin here. So that is the return pin instead of what looks like either another return pin or a transmission pin. And let's take a look at the waveform coming back from that detection circuitry. And there it is. It is actually demodulating that output signal correctly. So there you have it. That's the KTI Minisat Personal EPIRB, the old 121.5 megahertz analog models. And that was just a little bit of playing around with it. There could be some more interesting stuff going on in the circuitry and stuff. So if anyone's got a schematic, we'd love to see it. And if you want to discuss this, jump on over to the EEVblog forum. And if you like Teardown Tuesday, please give it a big thumbs up. Catch you next time.